Let's look at the element constraint for capacitance. For the capacitance here we have IC and V sub C labeled, and of course they are following the passive sign convention, right? So here if we use a differential equation, in that case the current would be equal to the capacitance times dVc dt. And if you apply the Laplace transform on both sides, we would have I sub C S. Of course, the I sub C S is just the Laplace transform I sub C T. I'm not going to write this anymore because we're following the same convention, even for the inductance as well. So in this case, we have a C times, and again here we're applying the differentiation properties. Right, so in this case, we would have S times the Laplace transform V sub Ct, which is the V sub Cs, and minus the V sub C 0. So that's the initial condition here, V sub C 0. Initial condition basically that the capacitor voltage at t equal to 0. Right, so that's at the beginning point. So this is the initial condition for capacitor voltage or capacitance voltage. Okay, and in this case we actually can write a the equivalent circuit, and in equivalent circuit in this case we based on current, so we're gonna use the KCL. So I have a total current here, I sub C S, and the total current, this has two components. One is not the inductance, one is so 1 over CS, and so this VCS divided by 1 over CS, so this is total V sub CS, and I'll have another component add negative CV0 instead. So if I do this, I would have a negative CV sub C0, right? So instead of doing the negative, so I flip the arrow and I get rid of this negative sign here. So I flip the arrow like this, and this is my equivalent circuit based on the differential equation, right? I can also do the integration equation or the integral equation, and in that case, what would we would have the V sub C T is going to be equal to the starting point, the initial condition of capacitor voltage, right? And plus we integrate from 0 to t, and that's going to be inversely proportional to the capacitance. That's I sub C, and I use dummy variable tau d tau. So in this case, this is basically from 0 to t, the overall charge, the change of a charge, the integration, right, divided by the capacitance, that's the voltage change. And in this case, we take the Laplace transform, we would have V sub Cs, that's equal to the V sub C0 over S plus the integration property, that's 1 over CS, right, times I sub C S, which is the Laplace transform I sub Ct. And in this case, I can also draw the equivalent circuit, right? The equivalent circuit in this case would be, I have some voltage there, so, and then I have the current, so this is quite straightforward. Let me draw here, and so in this case, let me draw here. In this case, I have the impedance. We haven't introduced the impedance concept. I have this component here, 1 over CS, and I have the voltage, and this voltage is going to be V sub C0 over S, right? And this is going to be the total voltage, and this is going to be total voltage V sub Cs, right? And pay attention to here, this voltage here. Let's call this, let me change the color. This is very important, because some of you use the equivalent circuit and find the solving circuit, everything did right, but when you do the inverse Laplace transform, you took the wrong term. So that's very important. So let's call this voltage across. Okay, and that's the V sub C prime S, which is this term, right? Okay, the V sub CT. So the V sub CT is the inverse Laplace transform of V sub CS. That's the total voltage of this one, not the other, not the inverse Laplace transform of the V sub C prime S, because this term here does not include the initial condition. Okay, so that's very important to pay attention to when you utilize the equivalent circuit. Okay, that's for the element constraint of the inductance. Okay, I'll see you in a moment for the concepts of impedance and admittance.